Welcome to today's Explainer. Today we're tackling something that literally sits at the very foundation of science. We're doing a complete breakdown of how chemistry's most famous grid, yep, the periodic table, is actually structured. If you've ever looked at that massive, kind of intimidating block of letters and numbers and wondered, is there a hidden logic to all this? Well, you're in the exact right place. We're going to decode that structure together, step by step, using a beautifully organized framework. It's going to be a lot of fun. Okay, let's dive into this. Our source material today is actually a handwritten master cheat sheet. Honestly, there's something incredibly powerful about stripping away those shiny, overly complex textbook graphics and just looking at raw, perfectly structured study notes to unlock this chemical code. They lay out the rules so clearly and so concisely that they're practically a blueprint for the entire physical universe. Right at the top of that notebook page is a prompt, and we're going to treat this as our core mission for the entire explainer. Quote, how are elements arranged in the periodic table? Describe periods and groups. I know, it sounds super straightforward, right? But answering this specific question unlocks the whole logic of chemistry. We're basically figuring out the exact rules of the neighborhood these elements live in. Section 1, Basis of the Arrangement. Before we can even talk about rows and columns, we've got to look at the foundation. These elements aren't just thrown into random boxes based on, when they were discovered or what color they are. Absolutely not. They're arranged strictly on the basis of their electronic configuration. It all comes down to the electrons. The way electrons are organized inside a single atom dictates exactly where that element is allowed to sit on the long form of the periodic table. It is a highly structured seating chart based entirely on element arrangement. Section 2, Periods, the horizontal rows. Now that we know electrons run the show, let's look at the grid horizontally. Just look at this number, 7. There are exactly 7 horizontal rows in the periodic table, and in the language of chemistry, these are officially known as periods. So whenever you hear a chemist talking about a period, they're just asking you to read the table horizontally, sweeping from the left side all the way over to the right. And here is where the architecture of the table gets really fascinating. As you move along one of these 7 periods, reading it from left to right, the physical and chemical properties of the elements actually change. You don't just get a row of elements that all behave the same way. Nope, you get a spectrum. The element on the far left of a period is going to have vastly different properties than the element on the far right of that exact same row. It's like night and day. So the crucial point is, why do they change so drastically if they're sitting right there in the same row? Well, it's because the electronic configuration is continuously changing within a period. As you hop from one box to the next, moving right, you're constantly changing the electron setup. Specifically, the number of valence electrons, those are the guys in the outermost shell, they decide the position. And because that outermost shell is constantly shifting as you move right, the chemical behavior of the elements shifts right along with it. Section 3, Groups, the vertical columns. Now, let's shift our spatial awareness and look straight down. Contrast our last number, 7, with this one, 18. While there are only 7 horizontal rows, there's a whopping 18 vertical columns, which is exactly what gives the table its wide rectangular shape. And just as the rows have a special name, so do the columns. These 18 vertical columns are officially known as groups. Think of it this way. If a period is a horizontal journey where everything changes, a group is a vertical drop where things share a really deep connection. And this brilliantly illustrates the genius of the periodic table's design. Let's pit them against each other for a second. On one hand, you have periods, horizontal rows where properties continuously change as you move left to right. On the other hand, you have groups, vertical columns where elements are placed specifically because they share similar properties. If you want variety, look across a period. But if you want elements that act like a family and react in similar ways, look up and down a group. The grid does 2 completely different jobs depending on which direction you're reading it. Section 4, Subgroups and Valence Electrons. To further classify these 18 vertical families, we're going to zoom in a bit. The groups are divided into 2 distinct subgroups, Subgroup A and Subgroup B, based on those similar properties. This really helps chemists categorize exactly how these elements behave and interact with one another out in the real world. Elements falling into subgroup A are called the main or representative elements. You can think of these as the elements that follow the rules most predictably. They're basically your classic examples of how chemical properties should behave, representing the standard, predictable trends of the table. Then we have subgroup B, defined as the transition elements. Now this is a critical distinction. These elements are the bridge. the transition between different parts of the table. Their electron configurations are a bit more complex, which allows them to form this incredible, wide variety of colorful compounds and unique metallic bonds. Now, what's really interesting about this slide is the ultimate secret key it reveals. The group number indicates the total number of electrons in the valence shell of the element. Just let that sink in for a second. The actual number sitting right at the top of the column, the group number, tells you exactly how many electrons are spinning around in that element's outermost shell. You don't have to guess. You don't even have to do complex math. The map literally hands you the key to how that element is going to chemically react, just based on its vertical position. How cool is that? Which brings us to our final thought. We started with what looked like a completely random grid of letters, but we've basically found the matrix. Isn't it profoundly elegant how the massive, chaotic complexity of the physical universe is perfectly organized by a simple count of valence electrons? 7 rows of changing properties, 18 columns of chemical families, all dictated by invisible electrons. Next time you see a periodic table, you won't just see a chart. You'll see the blueprint. Thank you so much for joining me on this explainer. Keep asking questions, and I will see you next time.